Hello everyone. So today we're going to talk about more hypothesis testing. So this is different tools for hypothesis testing. Now we're going to be talking about when you have two samples. And so we'll be comparing two samples from two potentially different populations. We're going to cover basically three main hypothesis tests. When you have two proportions and you have two samples and each one has a proportion, and you want to say something about the two populations from which the samples came. And then you've got two means, and you have two independent samples, one from each population, and you want to say something about how the two population means may differ. And then we're going to talk about two dependent samples. And that's where you have matched pairs. And that's a very useful test. Okay. So, inference about two proportions. So it'd be nice to motivate this with an example. Sure. So you have we see this a lot. You have two professions maybe. So right, teaching and legal services. Both very broad professions, and you want to know, does one have more women than the other? And so what you do is you take a sample from teachers, good random sample, and a sample from legal workers, law workers, legal workers, and you will get a proportion from each sample. The proportion may differ, but does it differ significantly? And we can do a hypothesis test to determine whether the difference in proportion is significant. So what you need is so P1 is the actual population 1 proportion. So the actual percent of teachers that are female. That's the true proportion. We don't know what that is. We're hoping to, decide something about that. N is the size of the population, of the sample size. X1 is the number of successes. That just means the number of how many people make up that population. So in this case, that would be number of women. P hat is the proportion, and Q hat is the complement. Okay, and then we do the whole same thing again, but with the other population. Now, hypothesis testing, it follows the exact same framework. In fact, it's a little bit easier because the null hypothesis is always just going to be given to you here. All right, so to start off with, we first identify the claim, and then we negate the claim, and then we choose a null and alternative hypothesis, and the null hypothesis will always be that they're the same. Now that may or may not be the original claim, so you still need to figure out what the alternative hypothesis is going to be. Maybe, and you really only have a few choices. It's either going to be P not equals to 2, P1 not equal to P2, P1 greater than P2, or P1 less than, greater than or less than P2. All right, and then you determine your significance level exactly as before, and then you identify the test statistic. I'm going to give you the test statistic right here. This is the test statistic you will use for this sort of a test. There. P here, this is called the pooled proportion. Notice it is the proportion of women in both professions. So successes among both samples. It's the best guess, assuming that the proportions are the same. So the fact that this thing here is being used indicates the null hypothesis assumption. We're assuming this. If that's the case, then they're both going to equal P hat. Okay. And then we find the p-value. It's normally distributed, so there's no degrees of freedom we need to worry about. And then we just make a determination. We restate the decision in non-technical terms. All right. Now, there's certain requirements that need to be met. First of all, the sample proportions are two simple random samples. Okay, they have to be random samples. If they're extremely biased, if you only queried women who teach at if you only sampled teachers from an all-girls school, the number of women is going to be much higher. And if you sampled lawyers from a legal service firm for women, that's also likely going to have a lot more women working there. Okay, and so those would be bias samples, and you can't infer anything really from those. The two samples, so the two samples are independent, and this is also necessary. So what does that mean? That means samples are independent if the sample values select from the samplation are not related in any way from each other. Okay. And then we need each of the two samples. For each of the two samples, there needs to be at least 5 successes and at least 5 failures. So what that means is that if I sample 100 lawyers, at least 5 of them need to be women, and no more than 95 of them can be women. So that's a requirement for this theory to hold. Okay, hypothesis test and pooled proportion. All right, so we'll talk a little bit more about pooled proportion. For tests of hypothesis made about two population proportions, we consider only tests having a null hypothesis of P1 equals P2. With the assumption that P1 equals P2, the estimate of P hat and P hat and P1 hat and P2 hat are combined. Okay, so you estimate that they're combined to make the here it is. To make the best estimate of the common value. So that's the best way you can estimate that common value, assuming that they're the same, assuming the null hypothesis. All right. Okay, great, wonderful. Let's take an example. Proportions of cars with rear license plates only. All right, so are the proportions the same in Connecticut and New York? See, so Connecticut and New York are contiguous states. That means they touch, both having laws that require front and rear license plates. The proportion, so both of them require front and rear according to the laws on the books. The proportion of Connecticut legal cars with rear license plates is only 239 out of 2,049, or 11.7%. The proportion of New York illegal cars with rear license plates is only 9 in 500, so that's 1.6%. The sample percentages of 11.7% and 1.6% are obviously different, but are they significantly different? Or is that just chance? I mean, is it really not that? Is there really a big variability in sampling? Okay, so continuing with this example, here's the data that has been found. And so what we want to do, okay, let's just go ahead and identify this. So we're going to answer this thing, but before we do, let's identify this data here. So we're talking about number of rear license plates. And so this right here is going to be X1. This will be X2. This will be N1. This will be N2. Here's P1 hat. So that's successes over total, which is this, always as a decimal. Don't ever use a percentage when you're doing math in an equation. And then this here's P2 hat. Okay, and they're giving us the 0.05 significance level of the p-value. Okay, and the p-value method, which is the only method we use to test the claim that Connecticut and New York have the same proportion of cars with rear license plates only. Okay, so it's the same proportion. So that's P hat 1. No, sorry. We're talking about the true population proportion. P hat 1 equals P2. Okay. All right. Let's go ahead now and get Excel open. So on the Canvas app, you will see in the sheets, you will see in the home page, there's a spreadsheet that you can download. So I have downloaded that and shared it to Excel. And this is what I'm going to use. All right, so I'm not going to copy and paste the question, but for your records, so you have it for an exam, it may be wise to do so. All right. So save a copy. Save. Click there. Step. Come on now. Okay. Splendid. All right. Step 1. The original claim. New York and Connecticut. Oh dear. Something like that. Have the same proportion of illegal cars? I think cars. Okay. The notation for that one is P1 equals P2. All right. Step 2. What's the opposite of that? So they're not saying, it's not saying that Connecticut has more or New York has less. It's saying that they're equal. And so the opposite of that is that P1 does not equal P2. Okay, step 3, the null hypothesis. For two sample proportions, the null hypothesis is always just going to be P1 equals P2. That's what we're testing. That's what we're going to assume. The alternative hypothesis in this case is going to be P1 not equals P2. All right, that's step 3. Step 4, identify significance level. Alpha equals 0.05. Let me just recall, I don't want to get that wrong. Yep, there it is, 0.05, right there. All right, go back. Oh, you know what? Let me go like this. There. That's nice, because I'm going to want my test statistic. Okay, step 5 now is test statistic. It is given to me in the above slides. Maybe I'll just write it in. Is that okay? Can I do that? Okay, enter. I'm going to write this in. Z equals P1 hat minus P2 hat over square root of P pooled, Q pooled over N1 plus P pooled, Q pooled over N2. Square root of all that. There's my test statistic. P pooled is X1 plus X2 over N1 plus N2. Alrighty, okay, that should be enough. Alright, so I'm going to need a few things here. I'm going to need X1. I'm going to go back down to my data here. Now, X1 is going to be 239, because that is the number of successes. Successes in this case are the illegal, are the cars with only rear license plates. And so that's that one. What about, how do I want to do this? N1 is going to be 2,495. Okay, X2 is going to be 9, and N2 is going to be 550. Yeah, great. Okay, so I've got that. That allows me to have P pooled. So I'll do P pooled is going to equal parentheses X1 plus X2, close parentheses, divided by N1 plus N2, close parentheses, enter. Okay, so there's my pooled proportion. Now I need Q pooled. Q pooled, and that's going to equal 1 minus P pooled. Enter. Okay, that's 1 minus P pooled. And if you want to look at P pooled again, though I really shouldn't, you can always pause the video and look at it. So there's P pooled, there's Q pooled. All right, what else do I need? No, I think that's it. All right, I put it all together and get Z. So Z, my test statistic is going to equal, okay, here I go, parentheses. Oh, I didn't get P hat. All right, my mistake. P hat is going to be, P hat 1. P hat 1 is going to equal X1 divided by N1. Enter. P hat 2 is going to equal, is going to equal X2 divided by N2. Enter. All right, great. Now that I've got all that junk, I can put it all together and make Z. So that's going to be P hat, equals, I forget. Oh, dear. there. All right, equals, parenthesis, p hat 1 minus p hat 2, close parenthesis, divided by what? Divided by square root of, I'll do parentheses. I really don't need to, but I'll do it anyway. P pooled times Q pooled divided by N1. Okay? Close parentheses, plus, open parentheses, again, P pooled times Q pooled divided by N2. Oh, that's X2. N2. There we go. Close parenthesis, enter. 7. All right. That's quite a z-score. Let me just look at that again. Okay, now, notice how I could click on it and I could see exactly what happened. On an exam, on the next celebration of knowledge, you will certainly need to do something like this when you have an Excel spreadsheet. You will lose points if I cannot click on the cell and see your formula, see what you did. So make sure we can do that. Make sure I can do that. All right, enter. I did it. I did step 7. Step 5, So step 6 now is going to be find the p-value. But what do I know? It's normally distributed. All right. And it's a two-tailed test. Okay, so p-value is going to equal, okay, now it's a two-tailed test, so I need 2. So here's my, okay, click the equals there. So here's my bell curve, my normal bell curve, and I'm way over here at 7 standard deviations. Now it is a two-tailed test because of this right here, the not equals 2. So I want this area and this area. Okay, now what I'm gonna do is I'm gonna find this area first. I'm gonna find this area and I'm gonna double it. Now the z value corresponding to that area is negative, right? Negative because it's less than the mean, which is 0. Z values are always standard normal. This is mean of 0, standard deviation of 1. So I'm going to use negative 7.07. It's exactly the opposite of this one. And I'm going to find my area to the left using norm.dist. And I'm going to multiply that by 2. All right, observe. 2, all right, equals 2 times norm dot dist. See, there's no right tail or two tail test with norm dot dist. So anyway, negative z-score, comma, let's see, what do we need here? 0, 1, cumulative 1, close parentheses, enter. Okay, there's my p-value. Step 7, p-value is less than alpha. If the p is low, the null must go. Reject the null. All right, now I'm going to put it all together. Step 8, I reject the null, so that means there is evidence. When I reject the null, I get evidence. When I don't reject the null, I don't get evidence. What do I mean by that? I mean, I can say, for my step 8 summary, there is sufficient evidence to conclude that the two states do not have a equal proportion of cars with both front and rear, license plates. All right, there it is. Okay, let's not worry about taking that screenshot. But there, I have completed this hypothesis test. Smashing. All right. Whoops. There we go. Okay, let's carry on. So, inferences about two proportion requirements. We talked about that. Where are we? We are here. Okay, so here's the interpretation according to the author of the book from which I took this example. We must address the original claim that Connecticut and New York have the same proportion of cars with rear license plates only. Because we reject the null hypothesis, we conclude that there is sufficient evidence to warrant rejection of the claim that the two proportions are equal. That is, there is sufficient evidence to conclude that Connecticut and New York have different proportions of cars with rear license plates only, which is the same as saying that their proportion of cars that have rear and front license plates is different as well. It is reasonable to speculate that enforcement of the license plate laws is much stricter in New York than in Connecticut, and that is why Connecticut car owners are less likely to install the front license plates. Okay, what can we do when requirements are not satisfied? Well, you know what I mean. Bad samples are bad samples. What we mean by that is that if it's not, I mean, if the sample wasn't taken well, there's no amount of statistical trickery that's going to fix that. If we violate the requirement that each of the two samples are at least 5 successes and at least 5 failures in a hypothesis test, we can use the Fisher's exact test. Well, that we don't have time to talk about that in class, but that's something that you could certainly look up and, given your training in this class, may be able to implement if you had to, right? If we violate the requirement that each of the two samples has at least 5 successes and at least 5 failures in a confidence interval, we can use bootstrap resampling methods. Okay, and that's something too that could be used. Okay, but let's go on now. Means now. So we talked about proportions. Now we need to talk about means, independent samples. Okay, and this is means when it's independent samples. Okay, two samples are independent if the sample values from one population are not related in any way to how two or somehow naturally paired or matched with the sample values from the other population. The alternative of that, the opposite of that, is dependent. And the two samples are dependent or consist of matched pairs if the sample values are somehow matched, where the matching is based on some relationship. So if one sample is husbands and the other sample is their wives, that is a matched pair. Another example of matched pair is you have students before a treatment and the same students after a treatment. The population of each is regarded as different because something has potentially affected it. The students before are not exactly the same as the students after. I mean, they're the same person, but they're different in a way. Okay. All right, notation. So two means. All right. So what's a good running example here? Is the average salary of teachers greater than that of the people in the legal services? And so, are they greater or are they pretty much the same? And so there's a mean. There's a population mean that you might be comparing two population means. Okay, so you have mu1 is the population, the actual population mean, which we do not know. The actual population mean of the first population, and one is the sample size of the first from the first population. X bar is the mean of the sample from the first population, and so on, right? We can read that. Okay, now what is this? Let's do the 8 steps here. Identify the claim, negate the claim, and then identify the null and alternative hypothesis. Now the null hypothesis, again, it's given to you. It's just going to be that they're the same. That's what we're really interested in. Are they the same, or is it different? Is the average GPA of Harvard different than the average GPA of Yale or Dartmouth? Yeah, are they different or are they not? And then we talk about the significance level, which is usually given, but if it isn't, we use 0.05. And then you need to identify the test statistic. And this is the test statistic that you will use. Yeah, great. Okay, and then we find the t-value, the p-value. Now, the p-value is a probability, so you use the distribution. In this case, it will be a t-distribution with the degrees of freedom. Okay, now there is a more sophisticated equation for degrees of freedom, but it is very complex. This little heuristic, take the smaller of 1 minus the 2 sample sizes, that's a very easy thing to compute, and it's fairly close and useful and conservative. Conservative meaning what? Meaning it errs on the side of a I may need to get back to you on this one. I'm going to guess and say that it errs on the side of a type 1 error. So that it's more likely to do a type 1 error than a type 2 error. All right. Okay, anyway, then once we've computed our p-value, we make our determination and we restate. Okay. Requirements. Sigma 1 and sigma 2 are not known, and we do not assume that they're equal. Okay, that's requirements for the following, for the above theory. The 2 samples are independent. Okay, they're not matched in any way. Samples are simple random samples. Simple random samples. Okay, and then you also need this sort of the large enough. The samples need to be big enough. So the 2 sample sizes are both large, as to say they're both over 30, or both samples come from populations having normal distributions. That would also be okay. All right, let's take an example. Listed below or on the spreadsheet that we downloaded are student course evaluation scores for courses taught by female professors and male professors. Use a 0.05 confidence level to test the claim that the 2 samples are from populations with the same mean, meaning that basically course evaluations for courses with female professors is the same as that of courses taught with male professors. Okay, does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? Okay, let's go to our data and let's go to our data. I'm going to go to course evaluations. Now this one's got a lot of data that we have to kind of comb through in a way. So first thing I'm going to do is I'm going to select all of this here. I would like to make my 2 samples, so I'm gonna, oh man, come on. Let's see, what do I do? Shift, okay, good, that worked. Okay, now, data, filter, show filter buttons. Okay, great, great, so there's that. Okay, now, professor gender. All right, there we go. It gives you the females and the males. All right, great. And now I need my, okay. So, and then we have the course evaluations in that column right there. Okay, let's go ahead and get started right over here. Step 1. Okay, what's the original claim? The original claim is I think that they're equal, right? I think that does it appear to test the claim that the 2 samples are from the same population. So we're saying that they're equal. So this is going to be the same population. So that means that the mean is the same. So this is going to be mu1 equals mu2. That's my original claim. The negation of that, the opposite of that, what is true when that is false, is that mu1 option equals does not equal mu2. All right. Enter step 3 now. And step 3 is the null hypothesis. Now the null hypothesis is given to me, and it is, let me actually, well, okay, mu1 equals mu2. We want to know if that's the case. And the alternative hypothesis in this case is going to be mu1 not equals mu2. All right, step 4, level of significance. Alpha equals 0.05, I believe is what they said. Step 5 is the test statistic, but that is given to me. Come on, there. That is given to me in the slides. Right there. T equals x bar 1 minus x2 bar over square root s1 squared over n1 plus s2 squared over n2. Notice that because mu1 and mu2 are the same, my true mean is mu1 minus mu2, and that equals 0. So some books you will see they have this written out. Okay, but I don't see what the point of writing that in is exactly because we assume that the difference between those is 0. Okay, so there's my test statistic. All right, so now let me start getting what I need. Uh-oh. Oh, because it's in draw? If I do home, will it? Okay. All right. So what do I need first? Well, I guess I need x bar. Okay, x1 bar. I'll just say x1 will be the females. So the female course evaluations. So the course evaluations with female professors, because those are on the top. Here I go. Oh, one more. Okay, that's them. Is it going to tell me how many there are? I wish it would. Okay. Oh, I forgot to do equals. Well, let me just look and see. So that's from 2 to 41. All right, so x bar is going to equal average from, well, course evaluations, B, 2 to 41. All right, there it is. So that's x bar. N1 equals, what is N1? I'll do count. That's what I'll do. I'll go like this. Up, up, up. I'll take this formula here. I will recycle it. Command V, but rather than count. Okay. 40. All right, great. And now what one do I need? I need S1. And so that is going to equal st dev s, because it is a sample. And then what I'm going to do, I'm going to do Control V. I'm going to paste that, but I'm going to, yeah, oh, man, Excel, come on. Get rid of that. Oops, oh, okay. All right, there. I think that's it, isn't it? Okay. Now let's do the same thing for the other ones. Command C, Command V. This is going to be X2, N2, S2. Okay, now all right, that looks good. Okay. All right, now let's talk about the with the male professors here. So that is going to be from 42 all the way to 94. All right? 42 to 94. Okay, where is it? I'm just going to write that in here. B 42 to B 94. Enter. Great. B 42 to B 94. And I'm just going to copy that actually. Command C. Enter 53. Oh. Okay, and there we go. All right, so there's that, what I need. Now I'm going to do T equals, I'm going to put it all together, X bar, equals X bar minus X1 bar minus X2 bar. Oh, I forgot my parentheses. I'm going to press left. It's going to wig out. All right. There we go. Good. Got my parentheses. Divided by square root of S1 squared divided by N1 plus S2 squared divided by N2 close parenthesis on the square root. Okay, -2. All right, that's all right. Okay, step 6, p-value. It's a t-distribution with the degrees of freedom of the smaller of n minus 1 and n minus the other. So degrees of freedom is going to be 39. Because 39 is n1 minus 1, and that is smaller than n2 minus 1. So now, the p-val is going to equal, and again, it's a two-tailed test. So I'm going to do 2 equals 2 times t dot dist t dot dist. It's a negative value, so I'm going to go for the left tail here. It's a negative t value. Degrees of freedom will be that one right there. Cumulative is 1, obviously. And because it's a continuous distribution, cumulative is always 1 for a continuous distribution. Press enter. All right. Well, that is quite a fine distinction. So, step 7. If the p is low, the null must go. However, the p-value is bigger than my alpha. And what that means is I'm going to fail to reject. Fail to reject. So, if I fail to reject, I don't get the evidence. So there's not sufficient evidence. So step 8. So, there is not sufficient evidence to conclude that the mean course evals for male teachers is different from that of female teachers. I don't know why it's centered. I'm gonna Control L. Oh, mercy. Oh, what? That is so weird. Let's go back. Undo that. All right. Okay, I'm fine with it being centered. Anyway, that's what it... No, I'm actually not. Let's see. Okay, that's fine. Click on the cell. Go to... There. There it is. There. Okay, that's better. All right, there it is. That was the second example. Grand. Come on. Come on. How do I... Oh, I had it. There we go. Oh, gosh. All right. Okay, great. So we did it. All right, now there's a few other situations here that I'd like to draw your attention to. So inferences about two means, independent samples. Okay, so two means, again, independent samples. But this time, the sigma 1 and sigma 2, they're not known. but you're pretty confident that they are equal, that the standard deviations are equal. There's no reason they ought to be different. So if that's the case, then you have this, you do this with the same notation that we've been using before, but now you have a pooled estimated standard deviation, and then you just follow this format. Notice the difference in the test statistic. You have SP squared rather than S1, S2, and the degrees of freedom is also different. But other than that, it is exactly the same. Okay, so there's the alternative. In reality, the population standard deviations are almost never known, but if they are, somehow, the test statistic and confidence interval are based on the normal distribution instead of the t-distribution. Isn't that interesting? So the next case, I'm not going to demonstrate an example on this case, just because it's not as important as the other ones. And then there's another case, which is where the sample standard deviations are known and equal. And if that's the case, you just use the test statistic given here. Do we need to know degrees of freedom? No, because it's a z. It's normally distributed. So there is no degrees of freedom. So you can find the p-value very easily. Just use norm.dist. Okay, here is a fairly useful table. Notice you'll recognize some of the test statistics that we have already seen. This right here, we've seen from chapter 8. This is also, wait a minute. Yeah, this is if the standard deviation is known. This one here is if the standard deviation is not known. We're going to talk about this one next. That's the paired differences. Here's equal variance, which is called homoscedastic, and then the heteroscedastic case, which is when the two variances are unequal. Okay. There's that wicked formula for the degrees of freedom that I was telling you about. But I prefer to take the minimum of n1 minus 1 and n2 minus 1. So take the smaller of those two to approximate your degrees of freedom. Okay, one last thing, and that's the matched pairs. So when designing an experiment or planning an observational study, using dependent samples with matched pairs is generally just a better way of doing things than using two independent samples. So you want to test whether a treatment improves performance. Just use the people before and after, and that'll be your matched pairs. Okay, so there's a bit of some new data, notation I mean. So D is going to be the set of differences between the two values in the single matched pairs. All right, so maybe mile time. Maybe it's a speed training, and you're interested of the distance of a mile. So mile time, the difference in the mile time of the matched pair. So before the treatment, I ran a 14-minute mile, and after the treatment, I ran a 7-minute mile, or an 8-minute mile. and so the D would be negative 6, 14 to 8, negative 6. All right, and so you have a bunch of D's. You can find a mean, the mean difference of the sample, and that would be D bar. Mu D is, we don't know what it is, right? That's what we're trying to talk about. And the question is on average, will everybody improve? Will D be positive or negative? What will D be? Okay. SD is the standard deviation of the differences, and N is the number of pairs of sample data. Okay, so here's the hypothesis test 8 steps. In this case, I'm going to use D equals 0. That's always going to be my null hypothesis here. And my, this is not correct. This is D hat minus mu D over SD square root N. That's the test statistic. It's a t-score, and the degrees of freedom is N minus 1. All right, let's take an example, and then we are done. So the example is going to be, remember that actress and actors data that we had? I have it here on Excel. I didn't want to write actresses and actors, so I just wrote thespians, which is a fancy word for actors. Okay, well, where's my data? Oh, okay, there. Okay. Thespians. All right, here we go. Okay, so these are matched pairs because they are the age of the recipients of the Best Actress, Best Actor, Best Actress awards in the same year. I think the first year was 1927. And so both the 22 and the 44 are both associated with 1927, so they are matched. All right, let's go back and take a look at the prompt. Okay, so data list ages of actresses when they won Oscars in the best category, in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. The ages are matched according to the year that the awards was presented. This is a small random selection of the available data so that we can better illustrate the procedure of this section. So we would just want to take a sample. Use the sample data with a 0.05 significance level to test the claim that for the population of ages of best actors and actors, the differences have a mean less than 0. So a mean less than 0. So that's the difference between the best actresses and actors. The difference is less than 0. So I'm thinking that's going to be actresses minus actors, and the difference is going to be less than 0. And so that means that actors are generally older. Their male counterparts are generally older when they win Best Actor. Okay. All right, let's go ahead and go to our thespian sheets. All right. So first thing what I want to do is, this is all the data. This is a population here because it represents everything. I don't want to do this on a population. So instead what I'm going to do is I'm going to randomize it and take a sample. In order to do that, I'm going to insert a column. I'm going to do equals rand. I'm going to fill it down. I'm going to copy, Command C. I'm going to drag, to there. I'm going to paste. There's my random numbers. And now I'm going to grab these here filter, show filter button, sort smallest to largest. Okay, it randomized, it mixed it all up because it was 2242, now it's 2162. And so that's all randomized, and I'm just going to go ahead and take the first 30. Anyway, I'm just going to take the first 30. Okay, when I do this. So let me just kind of, can I put that in a box? All right, so that's the data I'm interested in. Okay. Unfortunately, it's going to be very different from your data. Well, let's just see if we get the same thing. Okay. Step 1. See if we get the same conclusion. We ought to. That's the whole point of this theory, is that you ought to get the same conclusion without regard, irrespective of the random sample, as long as it was a simple random sample. So I'll be interested to see what conclusions we get. All right, so step 1. Step 1 is the mean difference in ages is between, I better say, in ages, between actresses and actors in the same year is negative or less than 0. All right, so symbolically, what does that look like? Symbolically, that would be mu d is less than 0. Okay. Step 2, the alternative of that is mu d is option greater than or equal to 0. All right. Step 3, the null hypothesis, H0 is going to be mu d equals 0. The alternative hypothesis here is going to be mu d less than 0. How did I know to do less than and not greater than? Well, the greater than one, the greater than or equal to, is the equals to one. So that one, greater than or equal to, that went to the null hypothesis. The original claim then goes to the alternative hypothesis. Okay, step 4. I believe they said alpha equals 0.05. Let me just check. Yeah, 0.05. All right. Step 5 now is the test statistic. Okay. There it is. Write it in. T distributed. T equals d bar minus mu d, which is going to be 0, over SD, the standard deviation of d, n, divided by n. Okay. So let's see. So d bar is going to equal, no. D bar equals there. D bar is going to equal, all right. So first what I need is my D's. D's. The differences equals actress minus actor. Enter. Copy. Just the first 30. Paste. Ooh. Paste. Okay, there, pasted it. Okay, so there's my D's. So that's what I'm going to take. The D bar is going to be the mean of that. So equals average all of that. Enter. Okay, yours will probably be a little bit different, I suspect. I don't know. Okay, what do we have? We have D bar. Mu D is assumed to be 0 because of the null hypothesis. SD is going to equal STDev dot S, because ours is a sample, a little sample of 30 years. Okay, so there's a standard deviation, SD. Okay, and then what do I need? I need N. N equals 30. Now it does, yeah, N equals 30. All right. Okay, and there's all that I need. So here I go. T equals parenthesis D bar minus 0 divided by parenthesis S divided by square root N. Okay, enter. Negative. So the test statistic is negative. So our data is 2 standard deviations. So I think we may be able to reject the null hypothesis here in favor of the alternative. But let's not guess. Let's make sure. So step 6 is p-value now. I better get degrees of freedom, and that's going to be 30 equals 30 minus 1. So let's do equals 30 minus 1. So you can look at that, 30 minus 1. Okay, now I'm ready for my p-value. And that is going to equal, is this a two-tailed test? No, it is a left-tailed test. And that's good because my t statistic is on the left tail. All right. So this is going to equal t dot dist, it's a left-tailed test, plug in my test statistic, comma, degrees of freedom, is that right there? And then cumulative, 1, obviously, and enter. All right, so there it is. Now my determination. Step 7. P-val is less than alpha. If the p is low, the null must go. And so the result is I'm going to reject the null. All right, and so step 8 here is, say I reject the null and I get evidence as a consolation prize. So there is sufficient evidence to support the claim. Or, you know what, there's sufficient evidence to support the claim that the mean difference between actresses and actors who won Best Actor and Actress in the same year. If you subtract those differences, the same year, let's see what it says there, that the mean of those differences is less than 1. Meaning, you don't need to write this. I'm going to write it though. Meaning in any, meaning in an average year, the best actor will be older than the best actress. We can say that with 95% certainty. All right, everybody. Hope that's all right. All right, have a wonderful day, and we'll see you later.